Hey folks, welcome back to another lesson, and we're almost in the final stretch here. So what we're going to look at today is explaining line spectra, and we're going to do that by building on the Bohr's model of a hydrogen atom. We're going to use that model to describe how emission or absorption spectra occurs. And then what we'll do is in the next and final lesson is we'll do some calculations on these line spectras. So there's going to be a wee bit of note taking for this lesson today. Okay, so first of all, just to remind you, a spectra, remember, is when you pass a beam of white light through a prism, and then that prism will cause the white light to split up into all the different colours that make it up. So remember that it was called dispersion, and it involves refraction. So a lot of physics kind of tying together now, basically. Okay, so in terms of line spectra, you've got lots of different line spectra. So first of all, the continuous spectra is one where you get all the light from that light source being emitted. And emission line spectra is where you only get specific bands of light being given out. And so the emission spectra is caused by when the electrons in the atom lose energy and photons are emitted. So those photons correspond to wavelength of a specific light or color, sorry, and that's why you get these specific bands appearing in our emission spectra. The opposite of an emission spectra is an absorption spectra. So this is where the electrons in the atoms absorb energy and photons are absorbed. And again, the photons are of a specific wavelength and frequency. So that's why you get these specific bands to kind of appear. Okay, if we put them all together, you'll notice that the emission and absorption spectra can complement each other, which means that if we were to add these two together, we get a continuous spectra again. Okay, now in order to explain line spectra, you may remember we couldn't really use classical physics or the classical model of the atom. We really had to use Bohr's model of the atom and Planck's quantization of energy. Okay, and you'll notice that Bohr actually got a Nobel Prize for being able to explain this. So let's do a wee recap on the Bohr model. So remember, the Bohr model has electrons orbiting at specific orbitals or orbits, and each orbit has a specific energy or quanta, and this is usually represented by this ladder diagram here. Energy are represented as horizontal steps. Now, notice these energy are in electron volts, but in your exams, they'll generally be joules. The second thing is, remember, there's a whole bunch of terms you have to remember about, for example, the lowest state is called the ground state, and then the other states are called excited states. Okay? The other thing to remember is that electrons can move between or transition between any number of levels. So they don't have to just drop one level at a time. They could drop multiple levels or in between these levels here like this. Okay? However, they must have the exact energy to jump from one level to the next, and hence quantization. So what I mean by that is if your electron was at energy level 2, it couldn't drop halfway in between 2 and 1. It has to drop exactly between 2 and 1 and give out that exact amount of energy. And this is what we mean by quanta of energy. It's got a fixed amount. That energy can be calculated using this equation, HF, where H is Planck's constant, 6.63 times 10 to the negative 4. F is the frequency, and E is the energy in joules. Okay, so that was the revision stuff. So given this is a hydrogen emission spectra, how can we explain the specific bands that we see in this emission spectra? Okay, so the specific bands represent a specific wavelength of light because they're a specific color. And remember, we have these equations that energy is quantized. So we calculate energy as E is equal to HF for a fixed F. And since the F is fixed, we know that the wavelength has to fix, and it can be calculated by using speed is equal to frequency times wavelength. And in particular, remember, this is all radiation from the electromagnetic spectrum. So we also know the speed of these waves as being the speed of light. So we're really tying together a lot of ideas now from the rest of the course. Okay, so let's explain how this emission spectra happens. So we start off with a typical energy level, and what we say is that the electron starts from an excited state. It's got to have energy, because remember, the emission spectra is when the electron lose energy emitting a photon. So it can only do that if it's at an excited energy level. Okay, it spontaneously emits that energy and drops to a lower energy state. Okay, and remember the key thing is it can only drop down a state if it gives out the exact amount of energy between those two energy levels. It can't go halfway between N3 and N2 or N2 and N1, etc. Okay, this only happens with specific quanta of energy, and remember we can use these two equations to calculate it, which I'll show in the next lesson. So emission lines are of a specific wavelength. Okay, so having used that to explain emission spectra, can you now use the same logic to explain the absorption spectra? So we start with the same diagram, but notice the electron starts in a lower state or even the ground state, because remember in an absorption spectra, the electron has to absorb the energy. Okay, so electrons start from a low energy state. Okay, it spontaneously absorb energy and move to a higher energy state. So it go ups one. And remember, this only happens for specific quanta of energy. And again, we can calculate it using these two equations. And that means you get absorption lines of a specific wavelength. And just to show you, you can get some really quite beautiful spectras. This is from helium, neon, and argon. And finally, a gentleman called Frauenhofer actually recorded all the line spectra from the sun, and he identified over 570 lines which corresponded to the different elements which make up the sun. And that's how we know what the elements are inside a sun.